Wonderful viewers, welcome to Science and Spirituality. On today's episode, we will be continuing our discussion with our featured scientist from last week's program, Dr. Federico Capasso, a Robert L. Wallace Professor of Applied Physics at the Harvard School of Engineering and Applied Sciences in the USA. Over the years, Professor Capasso has become primarily known for his pioneering work on novel quantum devices, such as avalanche photodetectors, which are light sensors that process optical communications to electrical signals, resonant tunneling diodes, ultra-fast transistors, quantum cascade lasers, and other semiconductor devices. Recently, he made a splash in the scientific world when he and his research team observed a repulsive, instead of the normally attractive, quantum force from the so-called Casimir effect. A possible future application of this phenomenon is the ability to make nano or extremely small objects levitate. This new finding was the cover story of the January 2009 edition of the prestigious scientific journal Nature. In an interview with Supreme Master Television, Dr. Capasso explains more about this important discovery. Now let us join the discussion.
In 1948, a relatively famous Dutch physicist by the name of Casimir. He had been working with Niels Bohr in Copenhagen, world-famous physicist, and he was working then at the Philips Research Laboratory. And there were some data in the lab they could not understand. So out of an interesting chain of thinking, Casimir, out of the blue, came out to propose his famous Casimir effect. You take two metals. There is no charge on these two metals. The two metals are my two hands. Yeah. Now we know that if there is positive and negative charge, they attract each other. Mm-hmm. If there is the same charge, positive and positive, they repel each other. Yeah. Now he says, take two neutral metals, put them close enough. What does it mean close enough? 100 nanometer distance, so 1 nanometer, 1 billionth of a meter. Then he says, quantum mechanics tells you that they will attract each other even though there is no charge. When he proposed this, some people were thinking, this sounds so crazy, and the math was kind of very difficult. But then he provided a physical explanation.
In the old days of classical mechanics, a vacuum was what remained if you emptied a container of all its particles and lowered the temperature down to absolute zero. However, the notion of a vacuum has completely changed with quantum physics, as now we know that the vacuum is not empty. All fields, in particular electromagnetic fields, have fluctuations even in a vacuum with temperature at absolute zero. We call this vacuum energy or zero-point energy. The force discovered by Dr. Hendrik Casimir is another example of the spectacular manifestation of vacuum energy fluctuations. Professor Capasso next discusses the Heisenberg uncertainty principle and links it with vacuum energy and Casimir effect.
In quantum mechanics, there is not a state of absolute rest. So there is nothing like an atom at rest, a molecule at rest. Even if you are at zero temperature and you can go arbitrarily close to zero temperature but never reach it, there is an inherent motion that will never stop, no matter how you actually cool matter. These metal plates, if you look at one metal, it's true that the charge is zero, but in time, because of this continuous motion of the electrons, we know that metals have electrons that are negatively charged particles that can move around freely, and there is a background of positive ions. So the metal is actually neutral, but what happens is that the electron fluctuates because of this motion. So on these plates you have charge fluctuation. On the actual surface you might have an imbalance of charge. On one side of the plate you might have a patch of positive charge. On this side you might have a patch of negative charge, right? Yeah. On the other plate, which is in front, I will find the opposite sign of charge. I have positive here or negative here, okay. Positive here where there is negative here. Yeah. So there is going to be a small attraction because of this charge fluctuation. And the fascinating thing is between any macroscopic object. These forces are not only between metals. If I take a book like this and a book near here and I put it very close, mm-hmm. There is going to be, if I put them very close, a similar force, much weaker than in the cases of metal. So this is a universal force, the Casimir these Casimir forces that are between any macroscopic or microscopic bodies, starting from molecules, going up to a macroscopic thing.
When we return, we'll continue with the amazing Casimir force, which originates from quantum fluctuations or vacuum energy. Welcome back to Science and Spirituality, where we are exploring the Casimir force. Our guest today is Professor Federico Capasso, a Robert L. Wallace Professor of Applied Physics at the Harvard School of Engineering and Applied Sciences. The Casimir force is an important factor to consider when we try to scale down machines into such tools as micro-electromechanical systems, or MEMS, or even to nanoscale mechanical systems. The attractive Casimir forces could make things stick together and possibly jam the machinery. Micro-electromechanical systems are typically micrometer scale devices and are commonly used in many industries.
This is a micro machine that we made at Bell Labs. This was in 2000. I just had heard so much about the Casimir effect. It says, how am I going to measure it? Simple. I had my colleagues at Bell Labs make for me this micro-electromechanical system, MEMS. What is a MEMS? Is it important? Absolutely. Your airbag, I hope you're never going to have an accident, but if you all of a sudden crash or to suddenly stop your car, the airbag pops out and makes sure you don't crash against your steering wheel. And what controls this is a MEMS device. So MEMS are in everyday life. So essentially they are chips that have mobile part. You see, this is a C, so it's essentially made of silicon, but it's all gold. And then we got a sphere which is metallized of gold. Then we decide to move the sphere closer to this plate. Now you see this plate is designed to that it can rotate around this axis, right? Yeah. And so now if I approach this here, there'll be a Casimir force, an attractive Casimir force. So the sphere, as it gets close, will pull up and you have a seesaw effect, right? So now how do we measure the force? We show this force kind of in a colorful way by this here, by measuring this tiny rotation angle. This is an angle which is less than 1/1,000,000th of a degree. So we have to measure it by very sophisticated technique, by electrical method. So we measure this Casimir force between a gold sphere and a metallized gold plate as we vary the distance between the two. And this is the first part of the story. Then I started to think, now if I change materials, I change shape, I can design quantum fluctuation. Because this quantum fluctuation of matter depend not on the material. If you have gold, silver, other material change, they depend on the shape. And they depend also what is between the two materials. So if you somehow put a liquid between the sphere and the plate, things change. Suppose you take two metals, right, and you put them inside a fluid. Now you have two metals separated by fluid. And so this is showed here. So we did an experiment. Essentially, we lowered the sphere of gold towards a gold plate inside a fluid. It's not important what the fluid is. In this case, the Casimir force is always an attractive force. If you change the lower plate from gold to silica, silica is like a transparent glass. In fact, it's used in chips all over. It's a very common material, silica. And you keep the same liquid. Now quantum mechanics tells us that this force becomes repulsive. See, what we measured is this repulsive force. We did not demonstrate yet quantum levitation, but the editor and the reviewers of Nature were so excited about it, and they said, we want to put this on the cover, so you can also put what you want to do next, what your vision is.
A type of levitation many are familiar with is magnetic levitation, and superconductive levitation forces have already been successfully applied in high-speed maglev trains in Europe and the Far East.
Now, I cannot make maglev trains, because this is so weak, the force. But this can be very important for nanotechnology. If you make chips smaller and smaller with mobile parts, and the parts become closer and closer. At some point they can stick together quantum mechanically. Our vision is we can use this quantum levitation due to the repulsive Casimir force to keep parts away from each other. So if you like, the fluids here are like a quantum mechanical lubricant. Super lubricant, some people have called it. So the idea is we can use this subtle quantum mechanics due to fluctuation to try to eliminate static friction or stiction in future nanomechanical devices.
Our appreciation to you, Dr. Capasso, for your insight and vision and for giving us an overview of your research on the intricacies of the Casimir effect and your development of quantum devices. We look forward to more good news as you and your team explore the many wonders in our universe. Blessed viewers, thank you for your company today on Science and Spirituality. Coming up next is Words of Wisdom after noteworthy news. Please stay tuned to Supreme Master Television for more constructive programs. We'll see you next time.